Hello, welcome back. This is Dynamics number 14, my video lectures. I'm sure you must be enjoying it. I think for the last two, three videos I've been doing friction as a part of dynamics or the Newton's laws of motion. And I think I tried to give you the theoretical aspects of friction to a large extent. You can make a notes out of it. And then I went on to give the distinction between sliding friction and the rolling friction and the misnomers associated with that, and at the same time the misconcepts associated with friction also I tried to give you in my lectures earlier. Now I have also defined the coefficient of friction. I've also defined the angle of friction, how these two are dependent on the nature of the substances and the types of surfaces that you come across, and how this is independent of area of contact. I think some of these things we saw, the limiting friction and this. Now, one way to understand limiting friction is, what is the minimum force required for you to move the body? That is precisely equal to the magnitude of the limiting frictional force. In fact, the purpose of limiting friction is only to know the limits you will never ever use in any of the questions. And then one more thing is, in most of the friction problems, you always come across two limits, the lower limit and the upper limit. I'll keep discussing that at every stage. I'm sure you can follow that. You can't go and suddenly give, this is the value. But before I go, I want you to first look at only static friction cases. I'm purposely giving you this static friction cases. Okay? Now, the static friction. I already gave you how it varies, etc. The diagram, I think that determines most of the points that I have already discussed. And now, in each of the cases, we will write only what is the frictional force available. The exam, they will never ask you what is static frictional force. They always ask you what is frictional force. So you have to give. And let me first look at the horizontal aspect. Now this is M, N, Mg, Fs, F. I am applying a force F horizontally parallel to the incline, and the static frictional force is Fs. Obviously here N is equal to Mg and Fs is equal to F. It's a straightforward, simple case. What is Fs here? There is no force to displace this body. Always look for that. Does any force act lurking, hidden, not visible to displace this body? If so, find out what it is. There's nothing lurking there. Straightforward. Therefore, straight away I have taken that case. Now, I am pulling at an angle alpha. So this is N, this is F sin alpha, this is F cos alpha, this is Mg. N plus F sin alpha is equal to Mg, or Mg minus F sin alpha. Okay? Then what is this static frictional force? That is bound to be whatever you are applying, F cos alpha. Okay? One by one we will go. Now, The same horizontal, let me presume the surface itself is moving with an acceleration A. I have placed a, follow my arguments very carefully from now on. N, mg, I am not applying any force. I already told you that the sliding friction always opposes a relative motion. Relative to the surface you are talking about. Therefore, relative to means if you take pseudo forces, definitely we talk of relative acceleration. Therefore, it is better, imperative for all of you to always apply pseudo force technique in friction. It becomes fairly simple for you, nothing to worry. Now, if that is the case, what is this is the surface I said I am is accelerating, and the body doesn't slip. That means no relative motion. When you say no relative motion, friction between them is bound to be static frictional force. Let us see. What is the pseudo force is MA, and this is, you said it is still not slipping. So now the fundamental point is to find out the direction of frictional force. I want you to never get confused with this. You don't have too many options. It's hardly A or B type, a 50-50 chances. I'm trying. Now you see how to get that. Number one, if friction were not to be there, you read my argument, if friction were not to be there, in what direction the body could have slipped relative to this? Relative to this means if you move it, this will definitely move backwards. Opposite to that is your static frictional force. Is that clear to you? Is this clear? When I'm having a body placed on a surface, surface is accelerating with A, and this is not slipping at all. In such a case, I am looking at, if it is not slipping relative to this, that frictional force is static, and then it tends to slip in this direction of friction, and therefore frictional force is in the opposite direction. So your answer here is, without this also you can say the only real force in this direction is Fs, and this is also accelerating with A with respect to ground, is not the ground, is only a surface. So I can write Fs is equal to Ma also, so that the relative acceleration here is 0. I hope this point is clear to you. Okay? Right. We still look at the horizontal cases, First, initially we looked at how to move, etc. I'm looking at the static frictional force. Now, let me see. Here is a disk rotating with about vertical axis. This is the disk rotating with an angular velocity omega. At a distance, I place a body at a distance r, m. You know, n will act like this, mg will, because this is the body. mg downwards, n upwards. So n is equal to mg, there is no issue here. N is equal to mg. But, what is the frictional force? How do you get it? I told you. If friction were not to be present, if you place a body here, and you start rotating it, what could have happened? This will try to throw away the body. We see in many places. Another way, what is centripetal force? The net force acting on the body in the plane towards the center is your centripetal force. The only real force between this and this is frictional force. Why am I taking it as static frictional force? Because that there is no slipping between the two. That's how I have assumed right from the beginning. And so centripetal force is Fs. And Fs is equated to mr omega square. Fs is related to mr omega square. What is this scenario? Follow. There is already a disk rotating. There I am placing this body. I hope you have got this point. I am now going into a little more complication. Here is a disk, similar disk. At the same distance r, I have placed a body m. I have now subject this to alpha, angular acceleration. So with the time, at time t, what is your omega? Because alpha is constant, omega is equal to initial angular velocity 0 and alpha t. Okay? Now at time t, what is frictional force? Body doesn't slip. This is a very interesting case, my dear friends. You have to be very careful here. Look at this body. Look at this body. Now, you are subjecting it to alpha. And you are subject to angular movement or rotation. So, alpha means there is a tangential acceleration. How? A t is equal to r alpha is how it is accelerating. Okay? And the pseudo will be like this. This is how it is increasing its speed. Initially, I am talking about once it develops, there are two things that you can visualize. Here, I am looking at pseudo forces. One, because alpha is present, this body is subject to an acceleration, tangential, and because this is having an omega, there is a centrifugal force. Both are what? Pseudo forces. What is the net force? Mr alpha, this is whatever it is, centrifugal force. Centrifugal force always acts away and it is always equated to, it's equal to mr, not equated to, it is mr. Whenever they ask centrifugal force, mv square by r and mr omega square only. Whenever they ask centripetal force, never say mr omega square, never say mv square by r. How? You have to give the combination of all the real forces acting on the body towards the center in the plane. So this is centrifugal force and this is the tangential force, both are acting, and the resultant force is like this. I hope you are able to understand this. Right? Now, the frictional force will be like this. What is that? Because it is not slipping. If alpha were to be 0, it could have been directed towards the center. Since alpha is present, it will go on increasing in its magnitude. So what is Fs now? Magnitude. These two are perpendicular. Therefore, mr alpha whole square, mr omega square whole square. Now you said in a time t omega is alpha t. M will come out, R will come out. This is alpha square, alpha alpha square also will come out, 1 plus alpha square t raised to 4. Omega square, omega is alpha t, so alpha square t square whole square, alpha 4 t raised to 4. 1 alpha square, I took it out. So this is how you have got. Now this is the magnitude of the frictional force. That is how you have to give. Very important, very, very important. When they give such kind of concepts, look whether that body is subject to an angular acceleration or it is already rotating and you are placing the body. So I have tried to give you that in the previous example. You try to place it, you will straight away get only one part. Here if you place it right from the beginning, then it is subjected to 2, therefore you will get in this fashion. This is the net pseudo force, so opposite to that is you are going to get that. Because Fs minus all these forces, that is equal to 0. Net force is 0 because there is no relative acceleration of the body. This is a very, very important concept. Now, based on this concept only, I would take a rod, and I am now subjecting it to an angular acceleration alpha. Here, a small exact hollow cylinder, I have put it into this. So it is at a distance equal to r. Okay? It is at a distance equal to r. This is subject to alpha. Now let me presume no gravity. No gravity. Now, it's a very interesting case. For example, I have placed this cylinder like this. Now, this is rotating. Remember, there is no mg. So, there is no n in this because there is no mg. But what is happening? It is pressing like this. Therefore, on this body, n is like this. This rod is pressing this. Obviously, body is pressing the rod. But what am I interested in when I apply Newton's second law? What should I do? I must take forces acting on the body. So I am taking like this. So N is into the board. You get my point? N is into the board. Why is it pushing? Because this is subject to alpha and therefore it is subject to a tangential acceleration AT. And what is AT? This is R and this is alpha. So with the AT it is subject like this. So the force is M, acceleration is AT, therefore N is equal to MAT. Very, very crucial. I repeat. Now here is a body and I am now pushing this. So that is my normal force. and this is accelerating with a tangential. Therefore, n is equal to MAT. Or pseudo force MAT in the opposite. N is like this, there is no relative acceleration, so n is equal to MAT. Got the point? Now there is a very interesting thing. This is how you are doing it. Okay? If friction were not to be there, then it could have slipped off. I told you how to get the direction of friction. If friction were not to be there, in which direction the body has a tendency to slip? Opposite to that. So this has a tendency to slip away. Therefore, it is not slipping. So it's still static frictional force. So Fs. Got the point? Therefore, Fs is equal to mr omega square. And omega as usual is alpha t. I am avoiding complication. I am not taking mg here into picture so that I can get straightforward case. Fs is after a time t. This is your Fs. You got the point. After a time t, this is how you have to give it. N becomes mr alpha. Still I am discussing only static frictional force cases. N becomes mr alpha, Fs becomes mr alpha square t square. I hope you are able to understand this. I'm focusing on the static frictional cases. Now, horizontal cases we saw. Without going into the complications, I will go to a vertical surface. If it is fixed, I am pressing it with F. Therefore, this is normal force. And you said that body doesn't slip. Therefore, this is mg, and mg tries to bring it down. Friction prevents it. No slipping, therefore Fs. So here Fs is equal to mg and is equal to F. Now the same thing F alpha, F cos alpha, F sin alpha, mg, n, and this is, be careful here, Afs. Now, what is happening? Fs plus F sin alpha is equal to mg Rfs is equal to. Now this is very important. Follow this carefully. Let me say, mg is around 100 newtons, suppose. And F sin alpha is 80 newtons. 100 minus 80, 20. Fs, so plus 20. So the direction you took is right. So 20 newtons upwards. Okay. Now, if F sin alpha is equal to mg, be careful. If sin alpha is equal to mg, then Fs is 0. So, if mg is F sin alpha, Fs is 0. If mg is less than F sine alpha, or F sine alpha is more than that. That means if this is 100, suppose this is 120, then what should happen? The tendency for the body is to slip up. Therefore, frictional force will have to be done. I will give you all these cases here. F sine alpha mg, n f cos alpha. Here, f sine alpha mg, that is fs. Very interesting. N. So, mg plus fs is equal to f sine alpha, or fs is equal to if it is negative, downwards. If it is positive, upwards. You see, very, very interesting. One has to be very careful because the direction of frictional force can reverse in this case. I hope this is clear to you. Now, we worked on a fixed surface. Suppose if it is accelerating with A, I am placing a body of m, mg, and this is n is equal to obviously ma, or pseudo force ma like this, therefore n is equal to ma, whichever way you want you can do. And this is your static frictional force. So Fs is equal to mg, n is equal to ma. Likewise. Now, a hollow cylinder rotating with omega and placing a body on this. So, n, that is your n is your normal force, and that is nothing but centripetal force. Therefore, equated to mr omega square. This is mg fs. Remember, this should be always drawn at the interface only. So n is equal to mr omega square, fs equal to mg. I hope you are able to follow this. Okay. Now look. Alpha is semi-vertex angle. Let us say this is omega. Now here again there is a problem. You have to be very careful. Draw FBD first properly. Normal force. Now I am feeling that it is rotating slowly. Of course, mg will always act like this. So this is mg cos alpha, and this is mg cos alpha, and this is mg sin alpha. What about the frictional force? If it moves slowly, the tendency is to slide down, therefore static frictional force is up the incline. Okay? But when you draw this, look, this is the circle in which this is moving. That's how, or this way or this way, it is moving. Therefore, if this is n and this is, look, n, this is alpha, 90 minus alpha, that is alpha. So, n cos alpha, n sin alpha. See, how am I, why can't I do this and go ahead? You can. I will show you now. Wherever you get a doubt, don't think that I am doing according to my convenience. I'll explain it to you in a while from now. Alright, now this is as usual mg. If this is your fs, this is alpha. Therefore, this is fs cos alpha. This is fs sin alpha. The only acceleration present is in this direction. Therefore, it is better to resolve in that and in the perpendicular direction. So, what is centripetal force? N cos alpha minus fs sin alpha. And what is that equated to? If, say, this is R, this is L, this is H, and let this be small r, I would equate it to m r, omega square. And in this direction, what are you getting? I'll rewrite that here. N cos alpha okay, and then this one, this is n sin alpha plus fs cos alpha is mg. Two equations, I want to get fs out of it. And omega is known, fs and n. So you can probably eliminate. We'll divide this, m gets cancelled. N cos alpha into g. This is n sin alpha omega square. Brought onto this side, this is fsg sin alpha plus fs cos alpha r omega square, or n into fs into g sin alpha plus r omega square cos alpha. See, equation appears complicated, but the way you get is very simple. N g cos alpha minus r omega square sin alpha by g sin alpha plus r omega square cos alpha. Again you are getting a negative sign in the numerator. Now go back, I told you now. You rotate this cone much faster, then what is the tendency of the body to slip up? In which case, where do you expect this to move? This is expected to move down the cone. slide down the cone. So frictional force upward. If it is moving upward, the frictional force is down the incline. Okay? That means in this case, if Fs is positive, it is up the incline. That means what? G cos alpha greater than R omega square sin alpha. Now you see how these conditions are obtained. Never try to memorize them. Never. So what do you mean by this? Cos alpha take on to this side, right? Tan alpha is less than G by R omega square. So many ways you can give it, okay? Omega must be less than G by R tan alpha under root for the frictional force to be upward. For frictional force to be 0, for Fs to be 0, omega should be critical is equal to under root G by R tan alpha. Now the small r you can convert into H, L, capital R based on the geometry. I'm not interested in that. You can easily do that. And for Fs, negative R down the cone. Then omega C omega must be greater than omega C equal to G by R tan alpha. Here also it can be up the incline, it can be down the incline, and there could be a 0 case also. So even on a smooth, theoretically smooth cone, you can still make the body stationary provided this relation is satisfied. I hope this is clear to you. Okay? Right. Now, this is fixed. I'm still talking about Fs. I want you to be careful. So, Mg, N, tendency is to move down, therefore, Fs. So, Fs is equal to Mg sin beta. Okay? Now, look. Suppose this is plus A up or minus A down. In which case, pseudo force if I take Ma, this is N, tendency to move like this, therefore, static frictional force upwards. As before, if you do, N is equal to Fs is equal to sin beta. This if it is accelerating up or retarding down. Now suppose if I take plus A down or minus A up. What do you get? N is equal to M into G minus A cos beta M into G minus A sin beta. This is how you are going to get the equations if you accelerate it up or accelerate it down. Okay? Fine. Then there is a chance that n could be 0 when G is equal to A. Fs doesn't arise. I told you, if n is 0, question of friction doesn't arise. Because contact is lost. Now, if I take the same thing, I am subjecting it to an acceleration B. What are all the forces that you have? N, and this is MB, MG. Okay? So MB component is like this, and the MG component, there are two. This is beta, so MB cos beta, MB sin beta, and MG cos beta. This is MG sin beta. Now, presuming it is going very slow, the tendency is to slip down. So the frictional force is up. So how do you write now? Fs plus MB cos beta, or what is Fs? Now you will get it for yourself here. M common G sin beta B cos beta. You can see here. And what is N? Sum of these two. M into G cos beta. That is your N. And that can never be 0. But Fs can be 0. So, for Fs to be 0, these two must be same, or B should be equal to a case we already discussed in the case of normal force. And then for Fs to be negative. Negative means down the incline. Then what you should say? B must be greater than G tan beta. Less than G tan beta, up the incline. Equal to G tan beta, no frictional force. More than G tan beta, down the incline. Everywhere in these problems you come across these things. So be careful when you do this. Is this clear to you? Right. Now, what if I give acceleration in this direction? So MB, MG sin beta plus MB cos beta. This is MG cos beta. So this plus this is equated to this. Rn is equal to MG cos beta minus MB sin beta, and Fs is equal to sum of these two. but the moment n becomes 0, this body falls vertically down. No friction. Don't say I will substitute the values here. It is meaningless and redundant. I hope it's clear to you. Okay, we'll put a stop to this here.